So this is the second meeting on Chapter 8 review. Chapter 8 is on chemical composition. And we've done question 1, 2, 3, 4, and 5. And we are going to start with question 6 today. So the question is, the percent by mass of nitrogen is 46.7% for a species containing only nitrogen and oxygen. Which of the following could this species be? So we have NO2, N2O, and NO. So three different species that are made of just nitrogen and oxygen. And so knowing the mass percent of nitrogen in that species, we should be able to find out what is the formula. And so when we have those formula or models of the molecules, then we can calculate the mass percent, right? Because the mass percent can be calculated using the molar masses of the element and, you know, the formula. So the mass percent of nitrogen, and we only need to calculate the mass percent of nitrogen. For the first one is going to have this formula. Oops, sorry. Oh la la. Hold on. So the mass percent of nitrogen in NO2 will follow this formula. It's the mass of nitrogen in this formula, NO2. So just the mass of N in this compound NO2 over the mass of the compound NO2. And of course, it is implied here that it's the mass for 1 mole of the compound. So on the bottom here, it's the molar mass of NO2. And on top here, it's the molar mass of N, you know, the contribution of N in that molar mass. So we need the periodic table to get the molar masses. And so let's look at the periodic table. We have nitrogen here with a molar mass of 14.01 and oxygen with a molar mass of 16.00. So we will use those numbers. And so if we plug in the values, we get, so the mass of just nitrogen in NO2 is just 1 times the molar mass of nitrogen because we have only 1 nitrogen per formula. So it's going to be 14.01 grams of nitrogen on top. And then on the bottom, it's like calculating the molar mass of the compound, and it's 2 times the molar mass of oxygen plus 1 time the molar mass of nitrogen, because the formula has 2 oxygens and 1 nitrogen. And you multiply by 100 because this is a mass percent. So when you're calculating percentages, you need to multiply by 100. So the calculator answer is, so you do 14.01 divided by, and oh, please don't forget to open the parentheses when you're doing 14.01 plus 2 times 16, close the parentheses, and then multiply by 100. The calculator answer is 30.4499. And here, both molar masses have only 4 sig figs, so we want to keep 4 sig figs. Notice how the 100 is an exact number. It's never going to limit your number of sig figs in the calculation when you're multiplying by 100 for a percentage. So 4 sig figs means it's rounding to 30.45% of nitrogen in NO2, and that's a percent by mass. So we can see that this doesn't fit the value here for that species. So it's not NO2. So then you do N2O. And so you need the mass percent of nitrogen in N2O. So the formula will be the mass of nitrogen in N2O. So this time it's going to be 2 times the molar mass of nitrogen over the molar mass of the compound N2O times 100. So the numbers are the same, except you multiply nitrogen by 2 and oxygen by 1. So the when you plug in the numbers, let's see, where are we? Oops. Here. Sorry. So when you plug in the numbers, it's 2 times the molar mass of nitrogen on the numerator. So 2 times 14.01 grams of nitrogen, because we have 2 nitrogens per formula, over the molar mass of the compound. And so the molar mass takes 2 times the molar mass of nitrogen plus 1 time the molar mass of oxygen, because we have only 1 oxygen in this formula, times 100. Again, in the calculator, you do 2 times 14.01 divided, open the parentheses, 2 times 14.01 plus 16, close the parentheses, times 100. The calculator answer is 63.6528. Again, we need 4 sig figs, so that runs to 63.65. That's the mass percent of nitrogen in N2O. So it looks like this is not this again, because the mass percent that was given is 46.7. So it should be NO. So let's verify that. And this time the formula is, so you take the mass of nitrogen in NO, so it's going to be 1 time 14.01, and then over the molar mass of the compound NO. And that's 14.01 plus 16. So let's look at what it looks like when you're plugging the value. So it's 14.01 grams of nitrogen over 14.01 plus 16 and times 100. So if you do that in your calculator, make sure you use the parentheses for the denominator so that the calculator does the addition before it does the division. The calculator answer is 46.68, 44, etc. So it runs to 46.68. And that's the mass percent of nitrogen in NO. And we can see now that it fits the number, right? So the species is NO, because the mass percent fits this formula. So which of the following could this species be? It's NO. So be careful here, it's not no, it's NO, the nitrogen monoxide, because NO has a 46.68% of nitrogen by mass. So that's how you can identify a compound. Let's move on to question 7. And so here you are one that this is similar to the question 20 of your homework 8. So please use this as an example if you struggle with question 20 of homework 8 in sapling. So the question is, how many grams of barium are in 456 grams of barium 3 phosphorus 2? P is phosphorus. So we have this mass of the compound, and we want to know the mass of just barium in that compound. So percent by mass are useful in this case, right? If you know the percent by mass of barium in this compound, you use the formula to calculate the percent by mass of barium in barium 3 P2. Then you can calculate the mass that you should expect of barium in this total mass of the compound. So let's do that. And so let's calculate the percent by mass of barium in barium 3 P2. So because it's the percent by mass of barium, so you take the mass of barium in this compound. And so that means you will multiply the mass, the molar mass of barium by 3, because there is 3 bariums per formula, over the molar mass of the compound, because it's always for 1 mole of the compound here. So we'll take the molar mass of the compound on the bottom. So let's look at the periodic table to gather the molar masses of phosphorus here, 30.97, and of barium here, 137.33. So that's the numbers in grams per mole for barium and phosphorus. So 137.33 and 30.97. So let's plug in the values in this formula. So the mass percent of barium in barium 3p2 will be 3 times the molar mass of barium. So 137.33 grams of barium times 3, because there is 3 bariums in this formula, over the molar mass of Ba3p2. So it's 3 times the molar mass of barium plus 2 times the molar mass of phosphorus. So in your calculator, you do 3 times 137.33 divided, open the parentheses, 3 times 137.33 plus 2 times 30.97 times 100. Of course, you could also calculate the molar mass separately and just have the number here in the denominator. It's okay to do it this way as well. The calculator answer is 86.930, etc. So here, the molar mass of barium has 5 sig figs, but the molar mass of phosphorus has 4 sig figs. So that's why we are limited to 4 sig figs, and we will run to 86.93% of barium in barium 3 phosphorus 2. So when you have the mass percent, that tells you you can calculate the mass of barium by using these percentages, this percentage, and the total mass of the barium 3p2. So for this, you take this total mass of the compound, and you use the percentage. The percentage can be seen as the mass of barium for 100 grams of the compound. So that's how you should see that. It means 86.93 grams of barium in 100 grams of barium 3p2. That's what it means, the mass percent. So you can use this as a conversion factor, right? Because where I say in, you can say equal. You have 86.93 grams of barium in 100 grams of the compound. So you can use this as a conversion factor. And so you will start the calculation with the total mass of the compound. Yeah, so let's do it all over, because let's insert an equation here. So you would start by typing the grams of Ba3p2, and then you will multiply by the conversion factor that comes from this equality, which comes from the mass percent. And because we have grams of Ba3p2 in the numerator here, we want grams of Ba3p2 on the denominator. Let me just format this properly. It's going to be a 3 here. And that's P2 here. So we want to cancel grams of Ba3p2. So we want that on the bottom. So you want the grams of that. And so that's 100. 100 grams of the compound contains 86.93 grams of Ba. And that's it. You do this in your calculator. So 456 times 86.93 grams of barium divided by 100. And that's 396.4008 And if we cancel units of, here we cancel units of grams of the compound, so we have grams of Ba left. Of course, we need to run this properly. And we have the given amount here has only 3 sig figs. The molar mass of barium, it's, the mass of barium here is 4. The 100 is exact because it comes from a percentage, so it's exact. So only this is measured here. So 4 sig figs, but only 3 in the given amount. So we need to keep 3, and that's going to be 396, and that's it. What comes after the 6 is a 4, so you keep it like this. And so that would be the mass of barium in 456 grams of the compound. So we are ready to do question 8 now. And for question 8, we have pairs of compound. And the question is, which of the following compounds have the same empirical formulas? So we have the, molecular models, and then the molecular formula, right? The molecular formula is the formulas as you know them and as we have written them up to now, right? But we can simplify formulas to the lowest numbers of, you want the subscript to be reduced to the lowest proportions as possible. And so here for water, the empirical formula is actually the same as the molecular formula, because you cannot reduce a subscript of 1 to less than 1 because it has to still be a whole number. And if there is only 1 atom of oxygen, you cannot make it smaller than that. So then H2O empirical formula is going to be H2O. H2O2, however, has 2 subscript of 2. So you can simplify them by reducing, by dividing them both by 2, and you get HO, just 1 and 1. So that's what is the empirical formula for H2O2 is HO. So which of the following compounds have the same empirical formula? It's not this pair. Let's look at the next pair. We have N2O4 and NO2. So the empirical formula of N2O4. So you have a subscript of 2 and 4. You know that they are multiple of 2, so you can divide by 2. If you divide 2 by 2, it's 1, and 4 by 2, it's 2. So the empirical formula of N2O4 is going to be NO2. And you can see that the empirical formula of NO2 is going to be NO2 again, because you cannot reduce the subscript of 1 for nitrogen to a smaller subscript. So the NO2 empirical formula is the same as the molecular formula, NO2. So here we go. We have the same empirical formulas for those 2 compounds. So that's a pair that fits the question here. N2O4 and NO2 have the same empirical formula. Let's look at the next pair. We have CO and CO2. The empirical formula for CO is CO, because you cannot reduce that further to, you need at least 1 atom of each. The empirical formula of CO2 is also CO2, because again, a subscript of 1 cannot be reduced further. So they both have the same empirical formula as they have the molecular formula. So this pair, CO and CO2, they do not have the same empirical formula. It's CO and CO2 which are different. Is there another pair? Yes. So can we fit them here? No. So we have CH4 and C2H6. So the empirical formula of CH4 is going to be CH4 again, because the carbon has a subscript of 1, and we cannot reduce that further. So same as the molecular formula. C2H6, we can see that 2 and 6 are multiples of 2. So we can divide by 2. So C2, 2 divided by 2 is going to be 1. And 6 divided by 2 is 3. So the empirical formula of C2H6 is going to be CH3. And that's different from CH4. So they do not have the same empirical formula. So out of all of these, only the N2O4 and NO2 had the same empirical formula. So that answers question 8. Give the empirical formula for each of the compounds represented below. That's question 9. And we have different models here. Oops. So we need the empirical formula. Before we find the empirical formula, we will use the model to find the formula that the model gives us. And that formula will correspond to the molecular formula, right? Because these are all molecules. We can see from the key, the labeling of the colors, that we have only non-metals: hydrogen, oxygen, nitrogen, carbon, phosphorus. And so when non-metals are bonded together, they make molecules. And we can see here it's molecules. So let's find the molecular formula of the first one, that has blue and red balls. And the blue are the nitrogen, the red are the oxygen. We have 2 nitrogen and 4 oxygen. So the molecular formula is going to be N2O4. It's the molecular formula. And we've seen above how this can be reduced to NO2, right? You divide the 2 by 2 and it's 1, and the 4 by 2 and it's 2. So NO2 is the empirical formula for this first compound represented in A. In B, we have 3 carbons. Those black balls are the carbons. And then the white are hydrogens. And we can see 6 hydrogens. So that means the molecular formula will be C3H6. So C3H6, that's the molecular formula. And now we can see that 3 and 6 are multiples of 3. So you can divide by 3. So 3 divided by 3 is going to be 1. And 6 divided by 3 is going to be 2. So the empirical formula of C3H6 is CH2. CH2 is the empirical formula. So that answers that question for B. So in C, we have phosphorus in yellow and oxygen in red. I see 4 yellow, so that's going to be P4. And oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So P4O10 is going to be the molecular formula. Let's show that P4O10. It's the molecular formula. And we can see that 4 and 10 are multiples of 2, not of 4, but of 2. So we can divide the 4 by 2 and it's going to be P2. The 10 divided by 2 is 5. So P2O5 is the empirical formula. You can see here from P2O5 that you cannot reduce that further because 5 is not a multiple of 2. So that's why you can only reduce that to P2O5. So that's the empirical formula of that P4O10 molecule. D, in D, we have carbon, hydrogen, and oxygen. And I see 6 carbon in black, 6 oxygen in red, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And we list them in the order carbon, hydrogen, oxygen. So it's going to be C6, H12, O6. So C6, H12O6 is the molecular formula of this molecule represented in D. So 6, 12, and 6 are all multiples of 6. So we can reduce that by dividing all these subscripts by 6. 6 divided by 6 is 1. 12 divided by 6 is 2. And 6 divided by 6 is 1. So the empirical formula will be CH2O. That's the empirical formula for this molecule in D. And that answers question 9, which was to give the empirical formula for each of these compounds. So question 10, why is it that the formulas of ionic compound are always empirical formulas? For example, NaCl, K2CO3, Fe2S3, you can see that you cannot reduce them further, right? In NaCl, there is only one of each. In K2CO3, there is only one carbon. And then in Fe2S3, between 2 and 3, you cannot reduce further. So yes, for all ionic compound, the molecular formula is the empirical formula. And that's the way we find the formulas for ionic compound that wants that. It's, you know, the way we find the formulas that makes it this way. So when we are writing the molecular formula of ionic compound, we are already writing the smallest whole number ratios of the ions comprising the compound, right? We always try to find the smallest ratio of, you know, ions that will make this formula neutral. So we are already writing the empirical formula. That's what actually we are doing when we are trying to find the smallest ratio of ions that will make the formula neutral. By finding the formulas this way, it's a way of finding the empirical formula. But we call them molecular formula. I want to emphasize here that ionic compounds are not made of molecules, like you saw earlier here. These are molecules, right? These are all molecular compounds made of non-metals only. In ionic compound, we have a metal and non-metal, and they are in ions. And so the way they are represented cannot be represented like a molecule. Because it's actually crystals that are built from the ratio of ions necessary to make the formula neutral. And it's this ratio, this formula, that is repeated over in the 3 directions, you know, X, Y, Z. You get this same formula repeated over and over, and then you get crystals of that. For example, in NaCl, we have you know, for every Na plus, we have a Cl minus. So they are, you know, intertwined like that, and always one Na between 2 Cl, and always one Cl between 2 Na. And of course, if you look in all directions, it's like that. But of course, they will position themselves so that Na is surrounded only by Cls, right? If you look at Na, it's only surrounded by Cls. And if you look at the Cl, it's surrounded by only Na, right? Because that's how they are attracted. Positive and negative charges are attracted to each other. And so you build crystals like this. So I have this picture of showing the cubic crystals of sodium chloride. Sodium chloride really behaves like this. It's one chlorine surrounded by, you know, 8 sodium actually, and every sodium is surrounded by 8 chlorine. And so it forms this cubic crystal or cubic lattice that is repeated you know, over the distance, over the 3 directions. So that's why when you want to find the formula of an ionic compound, it has to be, you know, the smallest ratio of the ions that make up the formula neutral. So that's how we can justify this. Question 11. When 3.269 grams of zinc is heated in pure oxygen, the sample gains 0.800 grams of oxygen in forming the oxide. So, you know, zinc with oxygen will make a zinc oxide, if you will. And so knowing this, the mass here of zinc, the mass of oxygen gained in forming the oxide. So find the empirical formula for the zinc oxide that is forming. So when you have the masses like that, you know, the proportion in mass would not give you the correct formula, because an atom of zinc is much heavier than an atom of oxygen, right? If we look at the periodic table, zinc here is 65.39 and oxygen is only 16. So you cannot use the mass to find the proportions in a number of atoms. So what you have to do is change those masses into moles, because the formula is based on moles, or number of atoms put together. So we need to change the mass of zinc into moles of zinc. So that's going to be the first step. Change the mass of zinc into moles of zinc. And for this, we will need the molar mass of zinc. So here, 65.39 grams per mole, 65.39. So, okay, so you will start the calculation with the mass of zinc that is given. And we will use the molar mass to change that to moles. Because we have grams of zinc here in the given amount, we want to have grams of zinc in the denominator, because we want to cancel units of grams of zinc. And we said 65 point, sorry, I need to look again, 39 for 1 mole of zinc. That's the molar mass of zinc. So in the calculator, you do 3.269 divided by 65.39, and that's 0.04999. Let's keep 4 sig figs, because we have 4 sig figs in the mass here, 4 sig figs in the molar mass. So here from the 4,999, that's 4 sig figs. What comes after that last 9 is a 2, so that's how we round it. And that's moles of zinc. Okay, so we need to do the same thing with the oxygen. And according to the text here, we started with this mass of zinc, and when we made the oxide, we added this mass of oxygen. So that tells you this is the mass of oxygen. So let's change the mass of oxygen into moles of oxygen using this number, 0.800 as the given amount of oxygen. The molar mass of oxygen is 16.00. Hopefully you know this by heart now. So how do we use it, the molar mass? So we have grams of oxygen in the numerator here. So we want grams of oxygen in the denominator. And we know it's 16.00. And that's for 1 mole of oxygen. Oh, what did I do? Oh, sorry. So in the calculator, you do 0.800 divided by 16.00, and that's 0.05. So that's the calculator answer. You know, the 1 mole is exact. 16 grams of oxygen is 4 sig figs. And here in the mass of oxygen, we have only 3 sig figs. So let's keep 3 sig figs. Right now, we have only 1 sig fig. So let's add 2 zeros to show 3 sig figs. And the unit of that is moles of oxygen, because that's what we calculated. And to show how this will cancel, let me do it with the zinc here, how the grams cancel, and here how the grams of oxygen cancel. That's why we have calculated numbers of moles. Okay, so what do we do with those numbers of moles? So I told you a formula is using number of atoms or number of moles to, to be found. And so we will use those numbers as subscript. So we will write what we call a pseudo formula because, the formula cannot stay like this. So it's an intermediate formula. And we will use those numbers of moles that we calculated here as subscript. So for zinc, it's 0.04999. And for oxygen, it's 0.0500. So that's our formula. We cannot leave it like this. We need to make it better. And for this, we will use the smallest subscript and divide both subscript by that smallest subscript, right? Divide by the smallest subscript. They both have a very similar value. This, if you would round it, you would get the same value. But still, it's the smallest value. So we will use this value that we have for zinc and divide both subscript by that. So here for zinc, it's going to be the same number over the same number. So it's going to be 1. And as I said, this number is exactly is the same as what's on the denominator as well, because if you round the 0.0499, if you round it, it would be 0.05. So that means the empirical formula is zinc and oxygen, and they both have a subscript of 1. So that would make it the empirical formula. And you can check that this is a correct answer because zinc oxide exists. And if you look at the periodic table, zinc here is always a 2+ ion, and oxygen is always a 2- ion. Those are two predictable ions. And so one of each will make this a neutral formula. So it makes sense. This formula is the empirical formula, but it's also the molecular formula. So question 12. And here, notice how I tell you that it is similar to question 23 of your homework on chapter 8 on sapling. So if you struggle with question 23, then watch this example to do your homework. So it's similar to what we did above, but it adds layers of complications. But you will see it's not too difficult. So instead of having masses given to us, we have percentages, mass percent. A compound is 92.24%, and it's not saying here, but it's percent by mass of carbon and 7.76% by mass of hydrogen. So that's the mass percent composition of the compound. What is its empirical formula? So let's answer that question first, and then we will use the rest to answer what is the molecular formula. For now, we only need that to answer what is its empirical formula. So earlier above, you noticed how we used the mass and changed them to moles, because the formula needs a number of moles or a number of atoms. Here we have mass percent. Mass percent means it's the mass for 100 grams of the compound. So you can also tell yourself, instead of having mass percent, I have a sample of 100 grams of the compound. So that's how you want to approach this. Assume that your sample has a mass of 100 grams, and then convert the percentages into mass. So then the mass of carbon is going to be 92.24 grams. That comes from the mass percent. And the mass of hydrogen will be 77.76 grams, and that comes from the percentage here. So change the percentages into mass for a mass of 100 grams of the sample. So then it's the same process. We will change the mass of each element into a number of moles. So let's do carbon first. Calculate the number of moles of carbon from the mass. So we have 92.24 grams of carbon, and we want to calculate the mass. So we need the molar mass of carbon, and it's 12.01. So let's use the molar mass. And because we have grams of carbon in the numerator here in the given amount, we want grams of carbon on the bottom. And the grams of carbon we said was 12.01 grams for 1 mole of carbon. So you want the 1 mole of C on the numerator here. This way the grams of carbon cancel. And so it comes down to dividing 92.24 divided by 12.01. And that's 7.680. So let's see how many sig figs we need. We have 4 sig figs in the molar mass of carbon. You know, the 1 mole is exact, doesn't limit. 4 sig figs in the given amount of carbon. So let's keep 4 sig figs, and that's what we need here. What comes after the 0 is a 2, so we keep the 0, 0. And the unit is moles of C. So we have now our moles of carbon. Let's calculate the number of moles of hydrogen. So we do the same thing here, but with hydrogen. We start with 7.76 grams of hydrogen, which was given here. And we will use the molar mass of hydrogen to change that into moles. Hydrogen is here, and its molar mass is 1.01 grams per mole. So because we have grams of hydrogen in the numerator in the given amount here, we want grams of hydrogen in the denominator so that we can cancel units. You know, I can cancel, show how I cancel units here above for carbon. Cancel units here and cancel those units. But I'm not done, right? So what comes with the unit of grams is 1.01 grams of hydrogen here. And that's for 1 mole of hydrogen. So the grams of hydrogen cancel, and the unit left over will be moles of H. So let's calculate how much it is. 7.76 divided by 1.01, and it's a 7.683. So let's see how many sig figs we need to keep here. Both the given amount of hydrogen has 3 sig figs, and the molar mass has 3 sig figs. So we need to keep 3 sig figs there. So we can drop the 3. And so that's the number of moles of hydrogen. So now that we have number of moles, we can write a pseudo formula, right? A formula using those number of moles as subscript. And so it will look like this. We have carbon with 7.680 and hydrogen with 7.68. And notice how these numbers are actually the same. So now to write the empirical formula, because that's how to find the empirical formula here. We divide by the smallest of the subscript. And so here it doesn't matter, they are both the same. So we will divide those subscript by themselves. And it's going to be 1 for both of them, right? C1, H1, which we would write as CH because we omit the subscript of 1. So CH is the empirical formula of this compound. So that answers the first question of inside question 12 here. But we are given the information that the molecular mass of the compound is 78.12 atomic mass unit. So what is the molecular formula? So when you are asked the molecular formula, you need to be given the molecular mass, right? You cannot find it without that. So what we have is the empirical formula. And there is a relationship between the molecular formula and the empirical formula. And it is that, the molecular formula is n times the empirical formula. And we need to find that number n. That's for the formula. But now, if you take the mass, that number still holds. So instead of writing molecular formula equals n times the empirical formula, you can write that the molar mass of this formula, molecular formula, right? The molar mass corresponds to the molecular formula, is equal to n times the empirical formula mass, right? So we need the empirical formula mass. The empirical formula was CH. So that means the empirical formula mass is going to be just the mass of carbon plus the mass of hydrogen. So 12.01 grams plus 1.01 gram, and that's 13.02 grams per mole of this formula CH. So that's the empirical formula mass. The molar mass, we are given the molar mass above here. It says the molecular mass is 78.12 atomic mass unit. So what this means is that this is the mass of just one formula. But you know that the mass of one formula is the same number for the molar mass if you change the unit from AMU to grams per mole. So this number here that is given can be used as the molar mass. So we are told that the molar mass is 78.12. Actually, you can remove those spaces. So the molar mass is 78.12 grams per mole. So we have two of these variables, and we are looking for n. So to find n, we will take the molar mass and divide it by the empirical formula, right? You divide both sides of this equality by the empirical formula mass, and you will get n equal the molar mass over the empirical formula mass. So let's plug in the numbers. The molar mass is 78.12 grams per mole. And on the bottom, it's 13.02 grams per mole. Of course, the grams per mole cancel. And so in the calculator, it's 78.12 divided by 13.02. And that's exactly 6. The calculator answer is 6. Let me show how these two units here cancel. So n equals 6. And remember that n represents the number here that we will multiply the empirical formula to get the molecular formula. So that means we do molecular formula equals n times the empirical formula, so 6 times the empirical formula. And the empirical formula, remember, was just CH. So that means you multiply the subscript 1 by 6, and you get C6H6. So that's the molecular formula of this compound.